This elegant, infinite series hides a mathematical mystery, a critical threshold that acts like a switch. Our challenge: find the exact value c that controls a dramatic phase transition. Below c, the limit vanishes to zero. Above c, it explodes to infinity. What is this mysterious critical value? The limit as x approaches 1 is cumbersome. Let's simplify it with a substitution. We can set x equal to e to the power of negative t. As x approaches 1 from below, t will approach 0 from the positive side. Now, let's examine the term 1 minus x. For small values of t, we can use the Taylor series expansion of e to the power of negative t. The Taylor expansion of e to the negative t is 1 minus t plus t squared over 2 minus higher order terms. This gives us t minus t squared over 2 plus higher order terms. Now let's examine the reciprocal 1 over 1 minus x, which appears in our exponential term. For our asymptotic analysis, we need the expansion 1 over t plus 1/2 plus order t. Therefore, the exponential term splits into e to the negative 1 over t times a multiplicative factor e to the negative 1/2 plus order t. This is crucial. The factor e to the negative 1/2 survives in the limit and affects the exact multiplicative constant in our final asymptotic. With this exact expansion, our limit expression becomes e to the negative 1/2 times the limit of f sub a times e to the negative 1 over t. This constant factor e to the negative 1/2 doesn't change whether the limit is 0 or infinity, but it's crucial for finding the exact constant when a equals c. Let's substitute our definition for f sub a using x equals e to the negative t. This gives us the sum of n to the a times e to the 2n times e to the negative tn squared. We can now combine all the exponential terms into a single exponent. The limit is now of a single sum, whose terms depend on both n and t. As t approaches 0, this sum will be dominated by its largest terms. Let's find where they occur. The magnitude of each term is controlled by this exponent, which we'll call g of n. To find the maximum, we can treat n as a continuous variable and find the derivative with respect to n. The derivative g prime of n is 2 minus 2tn. Setting the derivative to 0 gives the location of the maximum. Solving for n, we find that the peak occurs at n equals 1 over t. This is the Laplace method. The Gaussian suppression e to the minus t times and minus 1 over t squared ensures only terms within distance 1 over square root t of the peak contribute significantly. Terms outside this window are exponentially suppressed and contribute negligibly to the sum. Let's visualize this. We'll plot the exponent function g of n for a small value of t, say t equals 0.01. As you can see, the function forms a very sharp peak. The vast majority of the contribution to our sum comes from the integers and right around this maximum. And just as we calculated, the peak is located at n equals 1 over t, which for t equals 0.01 is exactly 100. This visual confirms our strategy of focusing on the behavior of the sum around this peak. Let's rewrite the exponent to analyze its structure around this peak. We will complete the square for the terms involving n. First, let's factor out a negative sign. This gives us negative of the quantity, tn squared minus 2n. Now, factor out t from the parentheses. Inside, we now have n squared minus 2 over t times n. This expression is ready for completing the square. We add and subtract the square of half the coefficient of n. This gives n minus 1 over t squared minus 1 over t squared. Next, distribute the negative t back into the brackets. The first term is negative t times the squared quantity. The second term becomes plus 1 over t. The 1 over t terms cancel, leaving this beautifully symmetric form. Our limit expression now features an exponent in the form of a Gaussian, or bell curve, centered at n equals 1 over t. The peak occurs at an approximately 1 over t, with characteristic width 1 over square root t. Since this width is much larger than 1, we can approximate the discrete sum by a continuous integral. The Gaussian has width of order 1 over square root t, which is much larger than 1. The peak is at 1 over t, which is much larger than the width, making the sum-to-integral approximation valid. To make the sum-to-integral approximation rigorous, let's use a change of variables. Let a naught equal 1 over t and write n as a naught plus k. The sum becomes a sum over k, where the exponent simplifies to minus tk squared. For the main contributing terms where absolute value of k is at most m over square root t, we have n naught plus k over n naught equals 1 plus k over n naught, which is 1 plus order square root t. Therefore, n naught plus k to the a equals n naught to the a times 1 plus k over n naught to the a, which gives us n naught to the a times 1 plus order square root t. Now let s equal k times square root t. This transforms our sum into a Riemann sum for the Gaussian integral, with step size square root t. As t approaches 0, this Riemann sum converges to the Gaussian integral over the entire real line, giving us square root pi over square root t. Note that since n naught equals 1 over t goes to infinity, the lower limit 1 minus n naught goes to negative infinity under our scaling, justifying the extension to the full real line. Tail control. Terms outside the main contributing window are exponentially small, making our approximation rigorous. Using our slow factor approximation, we can factor out n naught to the a from the sum. Combining our approximations, the sum equals square root pi times t to the negative a minus 1/2 plus negligible error terms. Our complete asymptotic formula, carrying the e to the negative 1/2 factor from the precise expansion in step 1. For each fixed real value of a, our complete asymptotic formula shows the exact scaling behavior. We now have a simple expression whose limit we can easily evaluate. Our complete asymptotic gives us this limit expression, including the crucial constant factor e to the negative 1/2. Since e to the negative 1/2 is a positive constant, the limit behavior depends entirely on the power of t. The limit will be 0 if the exponent is positive, because t to a positive power goes to 0. So we set negative a minus 1/2 to be greater than 0. To isolate the a term, let's add 1/2 to both sides. This gives us negative a is greater than 1/2. Now, we multiply by negative 1. Remember, this flips the direction of the inequality. So the limit is 0 when a is less than negative 1/2. Conversely, the limit will be infinity if the exponent is negative, as t to a negative power diverges. This requires negative a minus 1/2 to be less than 0. Similarly, for the second case, we add 1/2 to both sides. We get negative a is less than 1/2. And again, multiplying by negative 1 reverses the inequality. This means the limit is infinity when a is greater than negative 1/2. The most interesting case occurs when the exponent is exactly 0. This gives us a equals negative 1/2, our critical threshold value. At this critical value, the limit equals e to the negative 1/2 times square root pi, a finite positive constant. Our complete three-case analysis shows the critical value separates 0 from infinity, with a finite constant at the boundary. Therefore, the critical value is c equals negative 1/2. Our complete result is that c equals negative 1/2, and at this critical value, the limit is the finite positive constant e to the negative 1/2 times square root pi. Thank you for joining me on this mathematical journey. If you enjoyed uncovering this critical threshold mystery, Please give this video a like and subscribe for more fascinating mathematical explorations.